Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you again, Lord, for these students. I just pray that you'd help us to use this time wisely, Lord. We thank you again that our righteousness, if we have any, Lord, is not our own, but it's yours. And we thank you for your grace and mercy to us this day, Lord. In your name I pray. Amen. I'm going to come back to this later. First, I need to tell you guys about sigma notation. So, what is the deal with summation notation? Now, this really shouldn't be the first time you've seen this, because we needed summation notation before just to set up the Riemann integral, right? So it's hopefully not an entirely new story, but let me just remind you. If we have, for example, the sum k equals 0 to n of a sub k, what that means is a sub 0 plus a sub 1 plus a sub 2 plus dot, 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 plus a sub n. Now, if you're like me, at some point in your life, you'll find this dot, 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 dot thing disconcerting and somewhat vacuous, and you're like, I want something more precise for a definition there. Well, there is a precise way of defining the finite sum. You can use recursion. So, recursively, the definition is something like this. The sum k equals 0 to 0 of a sub k, well, that's just a sub 0. And on the other hand, if we look at the sum k equals 1 to n of a sub k, well, that's a sub n plus the sum k equals 1 to n minus 1 of a sub k, and that's true for, I can't spell it, for k in the natural numbers. So there's a recursive definition of the finite sum. Probably the two most important properties of the finite sum. Number one, if I have a constant times the finite sum, right? That's like a constant times a naught plus a1 plus da 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 plus an. So what can you do with a constant times a sum like that? You can distribute it, right? By the distributive property. So if you distribute the c through, we get what? ca naught plus ca1 plus da 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 plus can, right? And then you can rewrite that as the sum k equals 0 to n of c a sub k. In other words, we can factor a constant out of a finite sum, or we can pull a constant into a finite sum like this. What is it? And I guess I don't really, I suppose I don't really need the parentheses here. I do sometimes, I have a tendency to overuse parentheses in places. It's not wrong, it's just not right. Lack of style. I mean, I couldn't take off points for you putting in extra parentheses most places. Some of you have already experienced that I will take off points if you don't put them in certain places. Parentheses mean things. They're not always optional. All right, 2. If we have two finite sums, say k equals 0 to n of a sub k, plus the sum k equals 0 to n of b sub k, Well, you can write these out, right? I mean, it's a0 plus a1 plus da-da-da-da plus an plus b0 plus b1 plus da-da-da plus bn. And then what do? I mean, it's just finitely many terms, right? So you just regroup things. This is the same as a0 plus b0, parentheses, plus a1 plus b1, parentheses, plus da-da-da, plus an, bn. Now the parentheses here I'm just adding for emphasis. I mean, real number addition is commutative and associative, and I'm using those facts rather freely here. And then, of course, you can rewrite this as what? Sum k equals 0 to n of parentheses a sub k plus b sub k. Some people don't insist on putting the parentheses there, but I just like them to be there. Whatever. Now, you might complain, well, you just gave me this like careful recursive definition, and then you proceeded to use this sloppy plus dot 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 notation to prove these things. If you appreciate that that's an issue, good. You're ready for higher math. But most of you don't appreciate that issue, and that's why I gave you the proof in the notation you're more comfortable with. All right? Now, we will use both. There will come a time where you cannot avoid thinking in this way. Okay, so don't just assume that, well, I don't like this, I'm just going to use this stuff over here. And I'm just always going to think this way, and I'm never going to think about that way. That's not going to work for you in here. You need to be able to think both ways. They both have their place. You know, this concise notation versus this expanded plus dot 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 notation, all right? They both have their place. Let me look at a specific example just for a second, and then we'll go on to the story over there. So, you know, just if I have the sum k equals 0 to 3 of, say, I don't know, k squared minus 2k plus 1, what would I get? Plug in 0, what do you get? 1. Plug in, what's k equals 1 gives you what? 1 plus 1. Oh, 0. Huh, funny. So k equals to 0. Here's k equals to 1. What do we get for k equals to 2? 4 minus 4 plus 1? Yeah. Yeah, k equals to 3, I get 9 minus 6, which is 3. 3 plus 1 is, did you tell me 4? Yeah. Woohoo. All right, so we got, looks like 6. Now, this is k equals 3, right? Of course, this is just a comment here. I'll put parentheses around it so you can see it's a parenthetical comment. One important idea with finite sums is that we can relabel the sums. And sometimes relabeling a substitution, a new variable, slight shift from what you're given can make things a lot easier to think about. In this one, I can look at this and I go, wait a minute, that's k minus 1 quantity squared. So maybe I should say j equals to k minus 1. If I do that, k equals to 0 gives me what? Minus 1, right? K equals to 3 gives me what? J equals to 2. So in this new j variable, I've got the sum j equals to minus 1 to 2 of j squared, which is, of course, 1, well, minus 1 squared, right? Plus 0, plus 1, plus 2 squared, aka 6. What's kind of a strange pattern in the k variable becomes sort of obvious in the j, right? So we can start finite sums at negative values if we want, right? Doesn't usually happen, but it could. All right, one last example here, and then I'll go on to series. Finding formulas for things is an important task. We might have something like this. How about this? Suppose I want to find n naught, n, and a sub k, for which the sum k equals n naught to big N of a sub k is equal to, and now I got to make up something interesting. Here's what I'll do. I'll do 1 minus 3 plus 5 minus 7 plus 9 minus 11 plus 13. There, I'll stop there. Not too adventurous here, this example, just to give you a flavor for this kind of question. Yes. Educated guessing, though, right? So the point is, you try to look at it, try to see a pattern, try to see if you can't see there's some kind of formula that unites these. For these, I see, well, first of all, I see it's something like maybe 2 times k minus 1, right? And that's going from k equals to what? 1, 2, all the way out to this would be k equals to 7. But it's not quite that, right? Because it's alternating plus, minus, plus, minus, plus, minus, right? So what do I need to take this formula to the k plus 1, but yes. And so there you have it. You can choose, basically you could say that what you have is the sum. We can re-express, let me call this thing L. I don't want to call it L, let me call it Pac-Man, all right. So we could re-express Pac-Man as the sum k equals to 1 to 7 minus 1 to the k plus 1 times 2k minus 1. Right? In other words, I have n naught equals to 1, and I have a sub k equal to minus 1 to the k plus 1 times 2k minus 1, right? And my n, my big N, is 7. This, of course, is by no means unique. You could just as well start the somewhere like at 0. Instead of using 2k minus 1, you could use like 2j plus 1, right? And you could let 2j plus 1 go from, say, 0 to 6. And instead of having, you'd have minus 1 to the j then, right? I mean, let me write it down rather than just saying it. Another answer you could write would be this, right? You can check. That's the same set of values. This is essentially section 12.1 of your text, okay? Mostly it's just an on-ramp so that you know what the summation notation means. Are we all good on that now? I hope. All right. So that brings us to section 12.2, where we begin with the definition of a series. What is a series? Well, a series, in short, is a sum of things without end, all right? So let me just give you the definition here. This is from your text. If as n goes to infinity, the sequence of partial sums, and here's that sequence, here's the nth term in that sequence, right? S sub n equals k equals 0 to n of a sub k, right? If that tends to a finite limit L, all right, then we write the sum k equals 0 to infinity of a sub k is equal to L. Furthermore, we say the series, which is this right here, converges to L. We call L the sum of the series. Right? This is everything in black is the convergent case, okay? On the other hand, if the nth partial sum, if S sub n, does not converge to L in the reals, all right, then we say the series diverges. Sometimes you could say it's a divergent series. Just, just to be clear, the series is this thing. And I say this thing somewhat ambiguously because this thing may or may not be a real number. In the convergent case, it's a real number. Its sum is L, right? But it doesn't have to be that. The sequence of partial sums could diverge to infinity. It could oscillate. It could do all kinds of crazy nonsense. So but the series is nevertheless defined. Series are defined whether they diverge or converge, right? There are two kinds of series, ones which converge and ones which diverge, right? But still, divergent series are series. Okay, and that's why there's a distinction between the series and its sum. The sum, if it exists, is a real number in our current context. Right? You could imagine series of complex numbers or matrices or functions or other things. This is a general concept, this notion of adding things together. If you've got some way of adding things and you've got some notion of a limit, you can talk about series. But anyway, let's be where we are and do what we're doing. We're talking about real series, so its sum is a real number if it exists. The sequence of partial sums, right, also, I defined, basically this right here is the definition of the sequence of partial sums, okay? A couple things going on. This definition is simultaneously defining the sequence of partial sums. It is also defining the sum of the series, and it's also defining converges and diverges, all right? So those really four things are being defined here. If you wanted to write the sequence of partial sums as a list, I have it up here at the top, right? And again, I would say technically that's the range of the sequence of partial sums, if you want to be picky. But the first thing in the sequence of partial sums is the first thing you're adding in the series, right? Then the second thing is the sum of the first two things in the series. Then the third term in the sequence of partial sums is the sum of the first three things in the series. And it goes and goes and goes. When you get to as the counting goes here, if I start at 0, right, this is actually the n plus 1th thing. It's annoying but true. So the n plus 1th term in the sequence of partial sums is this thing. Any questions so far? I will quiz you on this tomorrow. Because you have no hope of understanding any proof we go over here until you have appreciated what this is saying and how it works. And the first step on that road is to actually know what it says. Right? You can't understand what you don't understand until you at least know what it is that you're not understanding. If that makes sense. Anyway, if it doesn't make sense, you can earn points tomorrow by memorizing these words. It's in section 12.2 of the book, also, of course. I don't know. There probably is some way of logically maintaining the structure here and like making it more concise. But I'm not going to worry about that just now because I don't want to inadvertently remove some important content there. All right, a couple of examples. Oh, yes.
Make sure I'm understanding this, right? If it tends to like the finite limit L, like it says up there, you write it the way it is. Does that mean it also converges? Like when it tends to a finite limit, that means it converges, right?
Right. The black stuff is connected together. Yeah.
And then L is so.
I mean, if you want me to give you more to memorize, to make it more precise, I should say furthermore to be careful in this case. But let me not. I tried to just copy what's in the book word for word. It's almost word for word what's in the book. I think if I stopped and thought about this for about 10 minutes really carefully, I think I could condense it down about 30%. I mean, well, I must go on. We can think about if we can make this definition smaller, maybe tomorrow. Other questions? Yep.
What do you mean by the 1 plus 10 term? Like, what is that? I'm just kind of.
Oh, just count. I'm just counting. Like, this is the first term, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, n plus 1th term in the list.
Okay. So every time it goes n plus another.
Yeah, if we go in a sequence, we list them. I mean, it's the first term in the sequence, the second term, the third term, the fourth term, just that.
Okay.
But the thing that makes a series interesting, right, is the sequence of partial sums. It's a really special kind of sequence, right? I mean, it's a sequence which is built from some other sequence, right? You're adding together this a sub k sequence to get a new sequence, which is the sequence of partial sums. The convergence or divergence of the sequence of partial sums ultimately is what leads us to either say this series converges or diverges. One student asked me after class last time, he was like, isn't the series really just the sequence of partial sums? Yes, I mean, that's not an unreasonable viewpoint, okay? But we do also need this language. But a series is a very special kind of sequence, if nothing else. But I don't really think of a series as, I mean, as much as it's true logically that a series is a sequence in that sense, it's more than that, as you'll see, in terms of its application, its structure, the way it works. All right. So here's example 1. Example 1 is really easy. So I start with a simple question. What happens if you add 0 to itself infinitely many times? What do you get? 0. Like 0 plus 0 plus 0 plus 0. I hope 0, right? Let's see why. Wouldn't that be disturbing if it didn't work out to 0? That'd be weird. That would be annoying. What's that? I would break math, yeah. It would fit perfectly with math. Yeah. Well, we will soon see that you can add together infinitely many things which are going to 0 and yet not get something that's finite. But one day at a time. That's tomorrow. Okay, so a sub k is 0, right? So what does that make the nth partial sum? The nth partial sum, right, is 0 plus 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 0. I can personally calculate this for arbitrary n, not a problem for me. 0. So clearly S sub n is the constant sequence 0, which converges to 0 as n goes to infinity. Therefore, by definition of convergent series, the sum k equals 0 to infinity of 0 is indeed 0. Let me write that out in words just for a second here. I say these words, but you might not, I mean, you can hear me say them, but maybe you don't have a way to write them down yet. This is read the sum of 0 from k equals 0 to k equals to infinity. That's how I verbalize that. So like here, this is the sum, k equals 0 to infinity of 1. Oh, I said it the other way here. Sorry, it's a sum. Oh, let me stop. Anyway, now that I'm conscious of what I'm saying, I can't say it anymore. What have I done? Oh no, I asked a question I shouldn't have asked. Now I'm confused. All right, I'm being silly. Anybody any questions about number 1? Does that make sense? How about example 2? What if we add 1? Yeah.
You have k equals 0 and then 1. Is that just concerned with the term itself?
Yeah, that's I'm enumerating the terms. Like I'm saying this generically is equal to, I'm trying to match it up with the definition I wrote over here, which was k equals 0 to infinity, right, of a sub k. So I'm identifying that this a sub k is equal to 0, and that pattern continues forever and ever and ever, right? A sub k is 0 for k equal to 0, 1, 2, 3, 4. The next one, a sub k is equal to 1, right? Forever and ever. So what's the nth partial sum now? We have to add 1 to itself how many times? N plus 1 times. What's that? Yeah, because 0 messes up the counting. There's n plus 1 ones here because we start at 0, right? Well, n plus 1 sum, if you add 1 to itself n plus 1 times, you get n plus 1. As n goes to infinity, n plus 1 goes to infinity. So the sequence of partial sums diverges, thus the series diverges. Why? This is the very definition of divergence. I have done direct calculation of the nth partial sum to show convergence and divergence here. Okay? Let's actually look at an interesting example finally, okay? Number 3. Number 3 is very interesting. In fact, it is exactly one of your homework problems, yes. So here we have the sum k equals 0 to infinity r to the k, where r is a real number whose magnitude is less than 1. Absolute value is less than 1, right? In other words, the question is, what is 1 plus r squared plus r cubed plus dot, 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 dot? What's that equal to? Was there a question? All right, I don't know anything else, but just to try to directly calculate with the definition at the moment. So what do? I try to calculate the nth partial sum. So just like in the homework, I look at Sn, which is this, and then I look at r times Sn, which is that. I just multiply each one of these by r, right? So that gives me r, that becomes r squared, that goes to r cubed, that goes to r to the n, that goes to r to the n plus 1. When you take the difference then of the nth partial sum and the r times the nth partial sum, just like we were instructed to do in that homework problem, remember? We get a bunch of cancellations as I've illustrated here. Chunk, 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 chunk. It telescopes down basically. All it leaves you with is this 1 and this rn plus 1, right? Like so. Then what? You do algebra, factor out the Sn, so we have Sn times 1 minus r, right? And then we can solve for the nth partial sum. we can actually just solve for the nth partial sum. It's really, I can't emphasize to you enough how precious and unusual the fact is of these examples that we can actually explicitly calculate the nth partial sum. The lion's share of examples we'll ever look at in here, we will not be able to explicitly calculate the nth partial sum. It's a rare and precious thing to actually be able to calculate it. Anyway, that's where these convergence and divergence tests come into play in the upcoming lectures. Yes. So now, if we look at this, though, now that we have a formula for it, we know this goes to 0. Why? Because we're assuming that the absolute value of r is less than 1, right? So if you have the absolute value of r is less than 1, that goes to 0 as n goes to infinity, right? And all you're left with is this, 1 over 1 minus r. And there you have it. The sum k equals 0 to infinity of r to the k is equal to 1 over 1 minus r. This is the convergent geometric series result. Actually, the full geometric series result, I'm going to write in the corner over here in a second, but I'm trying not to clutter things. I mean, you could take this example and like multiply it by a constant, and that would actually give us what we usually call the geometric series, but I'm just going to focus here for a bit. And any questions about 3 before we go to 4? I will do an example here in just a bit. Won't be long. Now, on the other hand, if you have the same thing, but if your r is greater than or equal to 1, right? And r is usually called the ratio of the geometric series, okay? So if r is greater than or equal to 1, then we can show that this diverges. Let's see how. First of all, r equals to 1 is something we already did. R equals to 1 is exactly this guy, right? Because the sum k equals 0 to infinity of 1 is, think about it, it's 1 plus 1 squared. It's 1 plus 1 plus 1 squared plus 1 cubed plus 1 to the 4th plus 1 to the 5th plus 1 to the 6th plus 1 to the 7th plus 1 to the... You see what I'm saying? I mean, this is exactly the r equals 1 case. Stupid, but true. And we know that diverges. All right, so that's settled. So if r is not equal to 1, though, then the absolute value of r is greater than 1. We can still do this calculation. This calculation does not assume that the absolute value of r is less than 1, right? That only comes into play when we finally take the limit down here in the green. Same calculation goes through, same nth partial sum. But what happens as n goes to infinity in the case that the absolute value of r is greater than 1? Yeah, it diverges. If r is positive, if like r was equal to 2, it would blow up to infinity. But if r was like equal to minus 2, it would do something much more annoying. It would go like really, really big, really, really small, but negative. I mean, really, really large negative, really, really large positive, really, really large negative, really, really large positive, and back and forth and back. Anyway, however you slice it, this thing diverges. Hence, the series diverges. All right. So this would be an example of a divergent geometric series. Finally, there's a theorem which I don't think I'll prove today. I'll probably prove this tomorrow. But here's a little theorem that I'll use nonetheless. It's not hard to prove, but if you have a constant and you have a convergent series, all right, whose sum is L, then the series where you multiply each term in the series by c, so just multiply term by term c, this new series is also convergent, and its sum is c times L. In other words, it's the infinite analog of property 1 for the finite sum. We can prove it. We'll prove it tomorrow, probably. Yep.
So when you're working with them, it's legitimate to pull the C outside the sum, just like it is.
Yeah, I would say I would caution that that step is most legitimate in the convergent case, and that In the divergent case, it requires further comment on my part. I'm only stating it for the convergent case right now. But I probably don't need to qualify that comment. I think it's generally true. Now, anyway, an application of this theorem is if I have the sum k equals 0 to infinity, right, of ar to the k, then I just multiply the limit, this one, right? That's like L. Multiply that L by A, and I get A over 1 minus R. So if the whole thing is just multiplied by A every term, it's just A over 1 minus R. That's the sum of the geometric series. Again, I have to be working in the case that the absolute value of R is less than 1. Okay? All right, so let's actually do an example of that. Pretty famous example. 0.9999999. Okay, you get the idea. All right, repeating. All right. What is this equal to? Why? You what? Uh-huh. Ah, okay. That's a good answer. Let me show you another one. 0.9 plus 0.09 plus 0.0. I mean, the larger question is, why can you add things like you just did? Right? Why does it make sense to add decimals? Why is there such a thing as a decimal representation of a number? What is a decimal representation of a number? It's a sum of fractions where how many fractions are you adding together? For example, pi. 3.14159. Oh, I've already told you guys I make them up. There's no point in me going on. But if you think of it, it's an infinite number of things, right? In fact, when you say that pi is equal to 3.14, blah, 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 that blah, 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 blah is without end, what you're talking about is a series. You can't even talk about real numbers properly without understanding what a convergent series is. All right? In other words, you guys didn't really know what a real number was until today. It's one way you could look at it. Some people would say you still don't know, but I'm an optimist. All right, so the question then here is, this is A plus AR squared plus AR cubed plus dot, 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 for what choice of A and R? So if I write this out in long form, this is like A plus AR squared plus AR cubed plus dot, 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 dot. Okay, A is the first term that you're adding if it's geometric. So A is 0.9. And what's R? R, whatever it takes to get from one term to the next multiplicatively is the R. So like multiply by R has to get me to here. Multiply by R has to get me to there. And so forth. R equal to, I heard 0.1. Do you guys agree with them? 0.9 times 0.1 is 0.09, times 0.1 is 0.009, times 0.1 is 0.009, right? We have proved that such a geometric series converges. Well, we've almost proved it. I guess I still owe you that theorem. Fine, you got me. You can easily see that this argument can be multiplied by A, though, right? For now, as a temporary argument. Transitional argument, if you like. So A over 1 minus R, what's that equal to here? Well, that's equal to 0.9 divided by 1 minus 0.1, also known as number 1, yes, 1. So there you go. This is a proof that 0.99 repeating is equal to 1. these are in fact the same number. And when I say that they're the same number, I mean that they're equal. And for me, that's what it means for numbers to be equal, to be the same. I would tell you that 1/3 and 2/6 are the same number. Why? Because they're equal. Some people say that those are different numbers. I say that that's not a helpful comment for students. You could go back to the construction of real numbers where we make a distinction between 1/3 and 2/6 as different members in some equivalence class, which eventually gets lumped into the concept of 1/3. But golly, that doesn't belong in a discussion in calculus. Oh, I'm sorry. Oops. Okay. I shut up. Anyway, any questions about this? Yeah.
But then 1/3 and 2/6 can be the same because you divide 2 from the top and bottom of 2/6 and you get 1/3. But then this one,
I just showed you they're equal. They're the same number. Oh, sorry. Now, I suppose some people would say the sum of the series is 1, but the series is not 1, it's the series. And I don't know, sorry, I can't, whatever. I leave you to your internet battles. Let's see here. A good example for us to do in the time that remains would be the following. If I can find it. Ah, yes. The sum, I'll do number 3. Sum of 1 over k times k plus 3. Sum k equals 1 to infinity. We're supposed to determine if this series converges or diverges. And if it does converge, oh, no, sorry. He just says, find the sum of the series. Well, that's kind of boring, so we know it converges. Man. Well, that's all. All right, so the question, I guess, is equals what? All right. Now, so the first order of business here, guys, is to calculate the nth partial sum. Because, well, that's all we know what to do at the moment. First of all, is it geometric? Are all series geometric? No, lots of them aren't. This isn't geometric. What would it take for a series to be a geometric series, basically? If you look at this, right, if this is a sub k, if you have a sub k plus 1 over a sub k, what would you get if it's geometric? R. That's why it's called the ratio. If you take the ratio of subsequent terms being added in the series, if the ratio of subsequent terms is constant for all k, then it's geometric. If it's not, it's not. Geometric, of course, is nice because we already have this like formula. Question? Okay. That's cool. So let's calculate. This is clearly not geometric anyway. Okay, so k equals, what do we got? 1 to n, all right. 1 over k times k plus 3. All right, so what does this look like? Oh, I think before I start doing anything, I want to do some algebra. Can you guys help me out here? What kind of algebra do I want to do? How about this? K over k plus 3 is going to be equal to like a over k, right? Plus b over k plus 3, right? Partial fractions. So you guys help me out. What are a and b? just a second, I'll follow you. So you tell me A is 1/3. B must be, yeah. Okay. So that means we've got 1/3k, right? Minus what? 1/3 times what? K plus 3, right? Be like, oh man, you mean partial fraction still matters on the next test? I know. Sorry, I can't get rid of it. It's just there, you know? Because really it's not calculus, is it? It's really algebra. It's just algebra you might not know. All right, I hope you know it. I'm gonna be optimistic. You know it. Everyone knows it. Okay, so we just start writing things out, okay? What do you have? You got 1/3? Let me just factor out the third, because otherwise it's just stupid, right? So this is 1/3 times the sum. Let's not make life harder than it needs to be. K equals 1 to n, 1/k minus 1/k plus 3, right? There, that will make life easier. Leave that 1/3 out front. We got 1/3, and then you just start going. So we got what? 1 minus k equals 1/4, right? Plus what? Plus 1/2 minus what? 1/5 plus what? K equals to, where am I? K equals 1, K equals 2, K equals 3. 1/3 minus 1/6. Yeah, 1/4 minus 1/7. I think I've written enough. Plus, plus. And I usually like to try to maybe go to like up almost to the end. I'm not sure how many I need to write here. Let me be a little bit cautious. I'll do n minus 2. K equals n minus 2. 1/n minus 2 minus what? 1/n plus 1. Plus 1/n minus 1 minus 1/n plus 2 plus, let's see here, let me tell you what this is. This was k equals what? N minus 2, right? This is k equals n minus 1. Where am I going to? All the way to n, right? 1/n. 1/n plus 3. That's the end of the line. Now, I usually put this on a couple of lines and I'm writing it, you know, in the paper. I can't usually fit this in one line. It's usually a 2 or 3 line deal. What happens here? Do you guys see? Yeah, let's see here. How about, is there any natural enemy of 1? No. 1/4. Uh-oh, yeah. Cha-cha. Cha-cha. And then how about, is there any natural enemy of 1/2? No, that one survives. 1/5 though. Yeah, 1/5 cancels with something that it's right here. Okay. I didn't write it, but it's there, right? 1/3 survives, right? But 1/6 cancels with 1/6, which is written over here, right? And then what? 1/7 cancels with the later term, right? How about over here? Does anything, what survives on the other side?
Minus 1/n plus 1.
So this, and that survive, but these cancel? Yeah. So anyway, getting to the end of the story here, we have 1/3 of 1 plus 1/2 plus 1/3 minus 1/n plus 1 minus 1/n plus 2 minus 1/n plus 3. There's usually some kind of nice symmetry between the end and the front of the telescoping. Like it kind of symmetrically telescopes. As much as the front pushes in, the back pushes in, so it kind of, most of the expressions I can think of anyway are like that. I suppose you could have something weirder, but now what happens as n goes to infinity? Right, so this goes to 1/3 of what? That's 5, 6, 11/6. Am I right? 1 plus 5, 6, 11/6. So that's 11/18. So the sum of the series is 11/18. Because the reciprocal terms go to 0 as n goes to infinity. Again, we're very fortunate that we could actually calculate the nth partial sum. Let me show you one that you can't calculate. The sum, k equals 1 to infinity of 1 over k squared. In other words, 1 plus 1/4 plus 1/9 plus 1/25 plus da da da. This is equal to pi squared over 6. I assure you, if you try to calculate the nth partial sum for that one, well, if you can find a way on your own to do it, show me. I can definitely write you a letter. I probably should give you an A in this course, if you can show me that through elementary means. I think Euler found this in 17 something or other. It's 37, I don't know. It's one of these many things that was known a few hundred years ago. I know ways of deriving it, but not without machinery, which we don't have. Oh, I'm sorry. Why are you still here? Leave. Skedaddle. Get out of here. Your presence here sickens me. Leave. I haven't graded your test yet. Don't worry. I know nothing.
What was the point of doing the partial fractions? Couldn't you have just done it from 1 over k times k plus 3?
Yeah, you probably could have. But the partial fractions is nice because it may, yeah, that may have, I may have unnecessary, well, I was afraid that I wasn't going to be able to see it if I did this. It's been a while since I've done these. And I haven't had a chance to prepare this, so I'm just working it out on the fly. I mean, there's got to be something nice about doing partial fractions, but you're probably right. So if you just do it directly, you get what, like? Oh, so if you just do it directly, you have less fractions to think about, right? So you get like, I see. So you got like 1/4 plus what?
1/10 plus 1/18.
Oh, see, because if you did that, right?
Yeah.
You don't see the.
Yeah.
That's why.
Okay.
Okay, good. I stand by my.
Do you know if you'll have the tests graded before spring break, or
Oh.
does that seem improbable?
I don't know what's today.
Today's Wednesday.